In the last lesson, we looked at the role of the hippocampus in building cortical memories. Here we're going to ask the question, why does our brain go through this consolidation process? And there'll be a couple answers given here, just that the cortex has more storage space, and the hippocampus, of course, also needs to be refreshed, as we learned in the last lesson. Let's take a look at a hippocampus under the microscope. This is the rat hippocampus, a slice through the hippocampus, and it's been stained with a purple stain. So over here, high magnification, the little purple little splotches there, the little purple objects are neurons, the cell bodies of neurons. And so here we see the organizational structure of the rat hippocampus. Let's look at a human brain, a slice through the human brain, also stained with a purple stain. And we can see the hippocampus down here, and you can just see the relative size of the hippocampus compared to the cortex. The cerebral cortex is this outer part of the brain, and that's where the cell bodies are. And scientists estimate that there's some 16 billion neurons in the cerebral cortex. By contrast, in the hippocampus, 50 million neurons. So right off the bat, we see the hippocampus is a much smaller structure, fewer neurons, fewer synapses, so it's going to have less storage space for memory. Cortex, lots and lots of neurons, even more synapses, lots of storage space for memories in the cerebral cortex. So the cortex, large storage space. Now, we said that these neurons are low plasticity, so it's sort of a slow learning system. We got to activate these cortical neurons many times to make good, strong memory traces. But once you make them strong, there appears to be slow decay, and that makes sense for a long-term memory system. Down here in the hippocampus, it's a small storage space for memory, right? Fewer neurons, fewer synapses, but it's a fast learning system. High plasticity neurons can grow strong synapses with one trial learning. However, there's fast decay in those synapses as well. The memory traces will be erased during sleep in preparation for new learning. So we have an interesting system here. We've got a memory system here that is specialized for responding quickly to the events of the day. And we store the day's learning as memory traces in the hippocampus. But this system has to be refreshed because it's a small storage space. There's not a lot of neurons, not a lot of synapses. We can't keep maximizing all those synapses, then the structure will be unable to learn anything new. We've got to refresh this system. But what we do learn here, the memory traces that are formed here during a day's learning, are then used to strengthen the cortical memory traces. And these are the ones that we're going to keep for a lifetime. And if we can build up strong synapses in this system here, we will keep those memories for a lifetime, and they won't decay as quickly as the hippocampal memory traces. Of course, the decay of the hippocampal memory traces is for a purpose, again, to refresh the hippocampus for new learning. Let's go into a little more detail what it means for a hippocampus to be ready for new learning. Up top here, we see a hippocampus, and we've got some hippocampal neurons and a bunch of synapses. You'll notice the synapses appear to be sort of weak. It's some baseline level of strength, and this is a hippocampus that is ready to learn, because learning involves the strengthening of synapses, but we want these synapses to be weak to begin with so that they can be strengthened to store the learned information. So when we're awake and we're learning, we're in school, in a classroom, or we're reading a book or watching a video lesson, that learning involves strengthening some set of synapses among a population of hippocampal neurons that got activated by the learning session. However, the hippocampus being a small structure, there's a limited number of neurons. And then there's also a maximum amount of synapse growth that can occur between these neurons. So we've got a problem. Because it's a small system, we're in danger of saturating the hippocampus with the synapses that have already been strengthened. And if all the synapses get strengthened to their maximum amount, the hippocampus will no longer be able to learn anything new. So what we've got to do then to make this a refreshed hippocampus is that we've got to go to sleep. We've got to first use these memory traces to consolidate memories in the cortex. That was the first phase of sleep. And then in that second phase of sleep, we're going to weaken the hippocampal synapses again so that they can be strengthened again for new learning the next day. And that next day, it might be a second study session covering the same information, but we will have a refreshed hippocampus ready to process that same information, making a new strong set of memory traces here that can be used during sleep to do consolidation again. So we want to keep our hippocampus refreshed for new learning, but it means we've got to do that consolidation during the night to make sure we save those memories to the cortex. So back to this diagram, the day's learning. So the memory traces for what we learned that day, they're going to be used to strengthen cortical memory traces. So in a sense, consolidation is how the brain integrates the day's learning into the long-term memory system. So let's put it all together. Back with our diagram here again, showing the encoding, storage, consolidation, retrieval phases, with cortex on the top part of the diagram and the hippocampus on the bottom part of the diagram. The hippocampus has a smaller storage capacity for memory, but it's enough to store the day's learning. By contrast, the cortex is the large capacity long-term memory system of the human brain. Now, cortical memory traces must be strengthened. Remember, they start off weak. They've got to be strengthened by the process of consolidation so they can be retrieved without the need of the hippocampus. So these are strong cortical memory traces that can be reactivated by cortical retrieval systems. We don't need the hippocampus for retrieving this kind of information. The high plasticity hippocampus makes strong memory traces of the day's learning to be used during sleep to consolidate cortical memories. Again, the hippocampal memory traces are reactivated and are used to strengthen the cortical memory traces. That's the memory consolidation that happens during sleep. And then after consolidation, the hippocampal memory traces are erased to prepare for new learning. And here we see a refreshed hippocampus. Now, of course, we could learn something entirely new here, or we could study the same information a second time or a third time or a fourth time with the goal of building really strong cortical memory traces. And that's what it is to get a good education. In summary, why does the brain consolidate memory in the cortex? We consolidate memories in the cortex because there is more storage capacity in the cortex, and cortical memory traces decay slowly. In addition, the hippocampal memory traces are being erased in preparation for new learning, so we must save recent memories to the cortex before the hippocampal memory traces get erased.